Good afternoon. In this session today, we will discuss the urban regional features extraction using remote sensing data. In the previous lecture, when the course has started, we have tried to learn the remote sensing process. That is how the energy, whether it is active or passive, when it falls on the object, Earth's surface, and the reflected emitted energy is recorded by the sensor on board the satellite, and finally the signal recorded signal is transmitted back to the ground station from where it is converted into the data products which is later useful for interpretation and analysis and later the final product generation. So this entire process we have tried to learn on the 11th of February and the lecture is already available to you. Now let us go further. When this remote sensing data product comes to the interpreter, how to derive the information. Now there are various issues are there when it comes to the user end. We are often perplexed with what kind of resolution should we choose, bands, date of pass, scale, band combination, and finally what kind of interpretation skill one should have, what kind of method should one employ, and finally the information is arising from many sources, how to merge the information, and then finally this information how it should be used for some decision making process. Later the remote sensing data has also got usage in the time domain for the change detection. Now when it comes to the resolution, we have got variety of resolution, that is spatial, spectral, radiometric and temporal. When it comes to the band, we have got the product from panchromatic, multispectral, hyperspectral. Date of pass means the selection of the date of pass of the satellite is very important from the features interpretation point of view. Again, in the context of urban planning, we have got scale is the very serious issue when we are talking about the perspective plan to the regional plan to the development plan to the local area plan. Again, when it comes to the user, when he gets the product what he will get, either the product will be in the form of false color composite or in the terms of natural color composite as you see on the popular web portals. So we'll try to learn all these issues in this particular session today. Now, when it comes to the user should have, when it comes to the interpreter, the interpreter should have the primary knowledge about what kind of signatures are manifested based on the signals which are recorded from the object. Now, on this particular spectral reflectance curve, I've tried to map only the two features which are of major importance in the urban areas. First is the any kind of urban surface, let it be concrete, and the vegetation, which are in predominance in the urban areas. Now you see, one has to be carefully see the information which is recorded across wavelength region, starting from the optical to the infrared to the thermal and beyond. And now you see there are somewhere the peaks are there, somewhere the dips are there. They reflect how the energy is reflected once it is transmitted from the object to the sensor. Now you see there are some peaks which is there, which is available on the vegetation. We have got a sharp spurt on the near infrared region. Subsequently, there is some plateau, and following which there are some water absorption dip areas are there. But the concrete in general has got a plateau throughout, except at some places where the minor kinks are observed. Keeping this in mind, once you have got the knowledge of the spectral reflectance curve, now we can understand the user gets the data in two forms. Either the data will be hard copy or in the soft copy digital format. But these days, soft copy data is in vogue. Now, when it comes to the soft copy digital data, it is called as image. An image is composed of 2D array of picture elements, or in short we call it as pixels. Now each pixel has got some intensity. Intensity of each pixel is corresponding to average brightness value or digital number or radius. Now this, because the data is recorded across the wavelength region, now each satellite data may have more than 3 spectral bands if it is multispectral. So in that sense, we have to create the composite, and the usual composition is called false color composite, where the phenomena and the color what you see in the composite is unusual what you see on the ground, and there are some specific reasons are there for which we create the false color composite. We'll try to learn this. Now, basically what happens with the data which is recorded, say for example, maybe 2 or 3 bands in the optical region, then the near infrared region or the thermal bands, whatever, depending on the satellite or the sensor characteristic. Now, these 3 bands satellite data, which is seen on the graphic terminal of the monitor. This graphic terminal, each gun of the monitor is assigned to a particular band which is recorded by the satellite. Now this requires lookup table, that in short we call it as LUT. This LUT generation assign that we are able to accommodate the entire range of digital number available on the graphic monitor, and this way assigning the particular band to the graphic channel, we are able to visualize the false color composite. Now let us take how this false color composite is generated. Say for example, a given satellite data will have 3 bands. Say for example, green. So now you see, but here you are seeing it's a black and white image, because it's a instead of seeing the composite, you are seeing the individual bands of the particular satellite. You see the features here. You are seeing some typical urban area where the large vegetation area is seen and the built-up area is seen. Within the vegetation area, you are seeing some kind of pattern, some kind of texture. Now in the built-up area, you are seeing some kind of again pattern and texture. So this way, but only point here, this is a single band data which is recorded in the green band. We have got some information available. Now when you go to the next band, red band, again here based on the reflectance characteristic which is particularly sensitive, red band is particularly sensitive to the cultural features. You are able to, when you and next is the infrared band, and kindly recall the spectral reflectance curve where we have seen the, in the context of vegetation, there is a sharp spurt or the sharp rise in reflectance characteristics. So this way all 3 channels together, when it is put on the screen and through the graphics facility, we are able to generate the false color composite. Now you see here very nicely, you are able to see the vegetation, you are able to see the built up areas. Within the vegetation, you are able to see the all tree cover, grasslands, with other kind of vegetation cover. Within the built up area, you are able to see the rows of houses, and then also you are able to see the other features on the ground. This is a typical false color composite which is generated using the high resolution satellite data. Now normally the remote sensing scientists, they are used to false color composite. Only point here, you note, as you notice here, you may ask the question that why the vegetation is seen in terms of red. For this reason that the vegetation red color occupies the large range of color which is normally seen by the human eyes. This has creates a better, superior quality of interpretation capability at the user end. Now, but again the point comes, the common user, he is normally used to seeing the vegetation in terms of green. So what we do, the false color composite is converted into the natural color composite, so that we are able to see the features the way we are seeing on the ground. So this is one kind of color transformation is done. But only point here, if you go back, toggle the image back and forth, you are able to see then in here the interpretation quality is slightly inferior. In that sense, now when this kind of image is available to you, Now, at the interpreter side, now your person who has got the skill to derive the information, he may use one of the out of two techniques. He can use one technique for deriving the information. He may use the skill based either the image of photo interpretation or the machine based algorithms for deriving the information. Now, what if he is using the image of photo interpretation, that is the visual interpretation, this is how it is called, then he uses his or her knowledge and experience of real world to recognize objects using elements of image interpretation. Now, what it does, he keeps the satellite data hard copy on the light table, puts some kind of tracing sheet over the light table, and then what he does using his own skill and the elements of image interpretation, he tries to find out various kind of features based on his interest. Now, once he is using the machine processing, here what he can do certain kind of preliminary analysis, and that to reprocess the raw data so that it becomes a superior quality product, enhancing some part of the image which have aided advantage for the interpretation. Or what he can do, that the same digital data he can subject to some appropriate decision making algorithms that identify and classify seen objects into sets of information. Now, I'll put it once again. The two methods are there for the information extraction. First is visual interpretation, and the second method is digital image processing or digital classification. Now, the point here that each method has got some advantage and disadvantage. In the sense, because the machine-based algorithm cannot entirely substitute the entire skill which a skilled interpreter may have. In that sense, the features you are able to distinguish, visualize same thing automatically using the machine-based processing cannot be derived. Now, let us go first the visual image interpretation, and the entire today's session will be particularly dedicated to the from the urban or regional point of view. Now we have got a variety of keys of image interpretation. They are called as elements of image interpretation. They are tone or color, texture, pattern, size, shadow, shape, association, and also resolution. So now what we do, let us see each effect of each element of image interpretation. For example, the tone. Now tone is nothing but, because what happens, the each wavelength band of EMR recorded by the sensor can be displayed in shades of gray from black and white. Now these shades are called tones. They will be dark, light or intermediate. Like you see in this particular image, it is a black and white or a color composite. You are seeing variety of shades here. Now these shades will be darker or this will be lighter. Now based on you have got a priori knowledge about the area, that means before you start interpreting or classification, whatever, you have to collect the ground truth. So now you see we have got the built up objects or the vegetation objects. Now because you again look back the spectral reflectance curve, because the concrete surface has got the higher reflectance, that is why it is appearing brighter. But the vegetation has got the reflectance which is slightly lower than the concrete surface. So that is why it's looking slightly darker. Now within the vegetation we have got the signature which is darker, which is lighter. This is again based on the senescence of the vegetation or the vegetation characteristic. Accordingly, you can find out objects on the ground, and this how the tone helps you. Now look at the color composite. Now it has got certainly advantage compared to the black and white image. Now here you are able to see within the vegetation, but at least two kind of vegetation. One where you can draw the boundary, vegetation type 1, and second vegetation type 2. Beyond this large patch of vegetation, intermittent objects of the vegetation also you can see where very sparse, either this is contains some kind of grass cover or other reasons, or the vacant land it is there, we are able to find out the other kind of vegetated surface. Then within the built up area also we can see we can demarcate the plot boundary, because it is a high resolution satellite data. You can demarcate the plot boundary, you can find out the linear objects which are going in between the built up area, or you can find a linear object which is going in between the forested area. So this way you are able to, based on the tonal characteristics of the image, you are able to distinguish the features. Now keep in mind that we cannot substitute the computer here to distinguish the tones or the digital number available in the image. So, but in any sense, we have got, human beings have got the skill. What we do, we assimilate other kind of information which when we put together, we are able to interpret the image. So this way, the digital or the visual technique has got its advantage. Now let us look at the next element of image interpretation. Here now texture is next element is the texture. Texture is frequency of tonal variation which gives the impression of roughness or smoothness of the image texture. It takes into account the microtonal properties. Now you can call it, the image will be fine, medium, coarse or irregular. Now let us look in the context of urban planning. We have got the planned area or unplanned area. Planned area means where we have got the roads or the houses, they are aligned in a definite fashion. If they are not aligned in a definite fashion, then that is called as unplanned. So now within the planned area, we'll have got high density, low density. Within the unplanned area, we have got high density and low density. Now you see how the texture will help you in identifying the low density or the high density features. Now let us take a look on the next element of image interpretation, that is shape. Now the shape will help you tell you the what kind of feature is available on the ground. It may be an aircraft, it may be a playground, it may be some kind of architectural place, or it may be some kind of road alignment, so or the overbridge alignment. So this way your shape will tell you that what kind of feature is available on the ground. Now let us try to see the next feature, that is the size. Now size helps you in finding the dimension, and also you can find out whether the object is bigger or object is smaller. Now let us say the size, you can, using the size you can find out the length, breadth, area, volume. You can do a judgment based on comparison with the familiar features in the same area. Now let us take, this is the athletic ground somewhere a part of the city. Now we have measured using the tools which is available in the image processing software. We try to measure the perimeter of the track. So we have found the perimeter of the track is 401.5 meter. But based on other data set, we found that the length is 400 meter. We found that the difference between our measurement and the standard measurement available is close to, difference is 1.5 meter, and the accuracy is 99.61%. Similarly, they take the another area where the playground is available in a school in the city. Here we tried to measure the dimension of the playground. We found the dimension as 10.93 meter into 23.52 meter, and the standard data which is available, that is 10.97 meter and 23.77 meter. So this is using a very high resolution satellite data which is available for that area, and here the accuracy was close to 98%. So this is how, using the size component, you can find out dimension of the various features in the urban area. Next is the shadow. Now the shadow is particularly helpful for finding out building height, or also if it is beyond the urban area, you can also see the various kind of geomorphological features. But there is a catch here, that the deep shadows, what they do, they obscure the features in the vicinity. So this way, shadow is useful to find out the height of the structure, but in the same time, it also obscures the surrounding features. Next we have the pattern. The pattern is nothing but the spatial arrangement of objects in the image. This how you can find out, you see the two kind of pattern here. They are useful since many times will be required to map the complex features rather than the individual object. Now, next element of the image interpretation is the association and location. Now, let us take one typical example of a city where we have got HIG, MIG, and LIG and squatter development. Basically, you see this kind of arrangements are available in, it has got some location in part of the city. Normally, LIG and squatter, they are at the marginal land of the city. So this is based on marginal land. It may be a river or periphery of the city or somewhere where this kind of LIG and squatter development will be happening. So this way association characteristic is going to help you. Now the remote sensing data is available, as you know, in the variety of resolution. It may be a course where the entire city you are available in fewer, you can map the entire city in few pixels, or it may be very finer like you're seeing this kind of data set where you can pinpoint the individual objects or the individual buildings. So this way resolution is another characteristic. Now let us take how we can find out the typical characteristics of an urban area. Normally in the urban land use land cover, within the residential area, we try to find out the low density or the medium density. You see here we have tried to use the various elements of image interpretation. If it is residential area and low density, there will be a dark cyan color, tone, texture will be coarse, size will be variable. It depends on the what kind of, it is a built up area or institutional area or other pattern will be regular. Shadow will be small, shadows will be seen. Then the density of the development will be low, like what you are seeing, that you are seeing interspersed vegetated and the urbanized built up area, and it has got comparatively more amount of vegetation. So these are all somewhere we will have the weekend land also within the residential area. Now let us take another example, the residential area medium density. Here again the tone will be same, that is dark cyan. Texture will be coarse, size will be variable, smaller as compared to the institutional or industrial building, pattern will be regular, shadows will be small kind, shadows will be seen, but the density of development as compared to the low density will be slightly higher, it will be medium category, and comparatively less amount of vegetation will be seen. This is how we prepare the land use land cover map for a typical city. Now, this is about how we can interpret the remote sensing data visually. But often, see, when you have got the large area to visit, you have got large information database to create, and then also we have got the areas beyond the urban area, that is the regional area. In that sense, remote digital image processing has got a role to play. Let us try to see that how the digital image processing helps us. See, the digital image processing also helps you many ways in improving the visual interpretation. How? If you got the any hard copy image which is processed elsewhere and supplied to you, you do not have any opportunity to improve the enhancement. You cannot do not have any opportunity to highlight certain features or to suppress certain features. But what you can do, make a hybrid approach. That means you do certain kind of digital image processing, highlight the area of interest, then go for the visual interpretation. Or what you can do, you can entirely go for the digital image processing, for machine-based processing for feature extraction. Now let us see how the digital image processing helps us. It is typical high resolution satellite image. Here the false color composite is seen, but you see, because the shadow orientation of the shadow and orientation of the objects, whether it is the vegetated object or is a building or cultural object, you see because of the orientation of the object and the shadow what the object has casted, because of this reason object is appearing inverted. Are you able to see? Yes. Then what we can do, we can just rotate the image. 180-degree rotation we have done, and then what we call it as then topographic inversion is correct, and based on which the features is appearing correctly. That means trees are appearing as supposed to appear, or the built up and the buildings are appearing the way supposed to be. So this way, your interpretation skill, whether you are interpreting on the screen or you are using some other method, you are able to distinguish the feature better. So this way, we have found out this kind of digital image processing techniques, they help you better. Now let us see further what we do. Now we are trying to find out some kind of digital image processing that we'll try to learn in the later slides. We can do certain kind of enhancement. Now if you look, toggle back in the previous and this particular slide, if you apply some kind of edge enhancement, you will find whether it's a linear feature like road, or the inter-building spaces, or the object's boundary, they will appear finer, sharper if you apply some certain kind of edge enhancement technique. So this way, this is the domain of digital image processing, where using the techniques you can improve your image interpretation skill. Now you can also, as we have seen in the previous slide somewhere, that you can also generate the natural color composite using the color transformation technique. And also you can apply certain kind of resampling method, where you can improve your you can improve the interpretation skill using the resampling methods. And the common resampling methods are nearest neighborhood, what you are seeing here. Now the nearest neighborhood method, it is good for feature extraction digitally. Now if you want to learn further about nearest neighborhood, you can visit the textbook, but broadly what it does, from the input to output, based on the shortest distance method, it places the pixel. So this way you can employ the nearest neighborhood or bilinear interpolation or the cubic convolution. But the point here, the nearest neighborhood method, that is good for the when you are going for the further digital analysis, because that does not change the digital number of the pixel. But if you are employing method like cubic convolution, like you are seeing in this particular image, this is good for visual interpretation, because what it does, the feature boundaries will become sharper, your image interpretation skill will be better, but this is not good for subsequent digital image analysis for feature extraction. Now let us go further, that is image magnification. You see, the point here is, any image when you have got, you can zoom it, you can magnify it to certain extent. Like you see here, the same area of data which is obtained at 10 meter, you can maybe zoom to 30 meter. But when you are zooming to the 80 meter, the features boundary become blurred. You cannot see anything. That means each image with its inherent characteristics, the way the information is collected, you cannot zoom, you cannot have any other further information to beyond certain extent. Okay, so here the high resolution image refers to one with a small resolution size. Fine detail can be seen in the high resolution image. On the other hand, a low resolution image is one with a large resolution size, that is, only the course of feature can be observed in the image. Now let us take the example of the magnification. Why the magnification has got some role? Magnification has got some role means you can toggle seeing the synoptic view, or you can zoom some part of the image. So what it does actually, in the context of urban, see how the urbanization or the growth of the city takes place. We have got some nuclei here. You try to see where I'm focusing here, this is nuclei, where the large, because this particular is a road junction, where the 4 or 5 major roads, they are at this crossing, they are converging. Now because you try to see how all these objects, concentric objects, they are all how the city growth has taken place and compactness has happened over the years. When you zoom it further, this is our information is available at 1:5000. Now you see here, you are able to see the features better, because you have got the using the magnification, image and magnification or zooming facility, you are able to see the features boundary sharper or better. And again, that phenomena, what you could see, the synoptic view, that has gone. But what we have gained, that we are able to see the features better. That means when you've got the digital data, you can visualize because you've got a facility of magnification, zooming or reduction. So this way, your interpretation, seeing the adjacency or seeing the next feature or seeing the feature in detail, that means this all can happen when you have got the digital data. So this way, when you go further, you are able to, when you zoom it at 1:1000 scale, you are able to see the features better. And you see the same junction, how the different roads converging, and then how the concentric rings, arterial road within this junction, they're all are there over as the city has grown and the compact has happened. You see, in the context of digital image processing, the information, many information, what you normally say are not visible. For example, this is a typical power line. Can you see here? This is a typical power line. You can say that the power line, typical power lines, width of the power line or the wire would be a few millimeter. But even then, you are able to see on the ground. For the reason, there is a concept called contrast. And also any power line, when it is erected, below its surface we have got a ground clearance where the vegetation is cleared. So we have got a larger, though the power line will be few millimeter, but below its surface you have got the ground clearance also. But before that, you have got a feature called brightness of contrast. Basically what it does, because of this clearance, the features separation has happened. So that means though the power line is few millimeter only, but because of the contrast present in image, you are able to see. But how the contrast plays the role, because when you got the digital data and using the digital image processing technique, you can adjust the contrast, you can adjust the brightness, which is not available when you are using the visual interpretation skill. Then remote sensing data has also got advantage, the temporal. Now you see this one part of the city where over the period of 2003 to the 2010 to the 2015, how the stages, how the urbanization has happened. You see this is the IT park area in some city where the IT park, how 2003 which was not available, now 2010 it is highly developed, and later on now you see the stage of development in the 2015. Similarly, other features, urban features in the vicinity, which was in the previous, that was vegetated surface, how the vegetated surface is got converted into built up area, and this kind of temporal. Now, the point here which I want to make, using the temporal remote sensing data, when you have got, you can flip, you can pan, and then you can see the changes. So this way, the digital image processing has got some advantage over the visual image interpretation. But only point again I'll reiterate here, but that the computer cannot substitute the machine-based processing. Now let us take what are the various operations feasible using digital image processing. Now once you have got the digital image data, we can go to understand the image quality. We can carry out some kind of statistical evaluation. You can go for the image georeferencing. Then you can go for the image enhancement. You can go for the feature extraction, information extraction. You can do the multi-data set data merging using GIS. You can also go for the chain detection. Let us try to learn briefly. For detail, you can kindly refer some standard textbooks like digital image processing by the Jensen or many other authors. They are available, and you can see digital image processing. If you got the hard copy image, you cannot assess anything about the overall. You can do the image quality evaluation, but any kind of manipulation is not feasible. You cannot see the statistical what kind of mode, mean mode, median mode, measures of central tendency or central dispersion. You cannot find out. We assume the digital hard copy image which has come to you, that may be in the georeferenced form. But the point here, suppose you want to overlay this information to any other platform, any other projection, that is not possible if you got the hard copy image. But if you got the digital image, then you can go for the multiple types of image georeferencing. You can go for the image enhancement and sharpening. What you can do, you can subdue certain feature, you can highlight certain features. Then you can go for the image classification. As I mentioned earlier, if you got large area to play, large area to information to extracted, then the image classification is a better opportunity. Now this image classification will be pixel based, it may object oriented based, and the later you can also go for the accuracy assessment. Now let us try to see in the terms of image statistics. There are certain characteristics that can be drawn if you got the digital data. You can find out the mode. We know the mode, median, mean. So what it is, the mode is a value that occurs most frequently in a distribution. Median is a value which is midway in the distribution, and mean, and we know that it is the arithmetic average. Now only point here, out of the three measures of central tendency, mean is it is slightly disadvantageous to use, because in the mean, if you got some outlier, the outlier has got a higher weightage in the mean value. So this way, mean carries some disadvantage. And then subsequently, if you got the measures of central tendency, you can find out the measures of central dispersion. This will help you. Basically, this is going to help you if you computed the measures of central tendency and dispersion. This basically help you to find out range of data available. You can find out the contrast in the image. You can find out how I can improve the image the sharper. How I can highlight certain part of the image, or how I can subdue certain part of the image based on area of interest. We all know about the deviation. Standard deviation is computed based on the difference of each value from the population mean, and then taking the square under root, then you can find out the standard deviation. And then we have got the square of the standard deviation is the variance. Then you can also find out, you've got two pairs of data, that means two bands are available in the satellite data. Then you can compute the coefficient of variation, or also you can compute the correlation. So this way, covariance is the joint variation of two variables about their common mean. So I'll not get into the details of this, how to compute the covariance. These all are available in the standard textbook. But basically, how the covariance is going to help us, because basically it tells you that if you've got two or more bands in the satellite data, whether there is two bands, whether there is a redundancy or there is unique information which is available. Same way, the covariance and correlation characteristics, that's going to help you whether data is unique or some kind of duplicate is available. Now this is all about that is about the image characteristics, that means statistical information. Now once the data has come to you, the data will be needs to be rectified. Why the rectification? For the reason, because you have to convert the data in some certain kind of projection system, and also you have to correct some kind of error which has creeped in during the image acquisition process. Now the image rectification again is a huge topic which cannot be covered in a single integrated lecture like this, but broadly I try to tell you, image rectification, it helps you to remove all kind of inherent distortion which has occurred, which has got into satellite data due to image acquisition process, because of sensor, because of the atmosphere, or because of certain other reasons, so that data becomes error free, and also we can project the data to the other data sets which are already available with you. Let us try to learn what kind of errors are normally there in the satellite data. You see, what happens when the satellite is in the orbit, the Earth is also moving on its orbit. Now this rotation which is there from the west to east, at the same time satellite has passed from pole to pole. In that sense, in the descending mode, when this has happened, unintentionally the data is recorded in the rectangle form, but because the west to east movement of the satellite, that kind of the frame which is really recorded, that is a parallelogram. Basically, the satellite has sent the data to the ground listening station like a rectangle, but because of the west to east movement, that has to be parallelogram. So what we do, if we know the speed at which the earth is rotating on its axis, in that then you can find out certain, then you can correct the data to account for the earth rotation effect. Next is, for I'm just throwing the light on the some basic error which creeps in because of the varying reasons. Another one is the panoramic distribution. Now the panoramic distortion means basically what happens when you're looking at the nadir, that means below the sensor, the pixel which is below the sensor, there is no issue. But the objects which are off the nadir, that means which are not directly below the sensor, there will be some kind of curvature phenomena like the earth which has got curvature. So the curve, the feature which is the extreme end, that will have a larger pixel size. Larger pixel size means that actually the pixel what you have recorded by the satellite on the ground, that will be larger. So this accounts for the panoramic distortion. This needs to be corrected. Next is the variation is the platform altitude, altitude and velocity. Now here what happens, because when the satellite is in the orbit, there are varying reasons are there which causes error in the observation, and this will be perturbation in the satellite altitude or the attitude or the velocity, which may change what we call it as pitch, roll and yaw correction. So this needs to be corrected. Now all these kind of error which creeps in either due to sensor mechanism or due to atmosphere, that can be corrected with a process called rectification using the ground control points. Now the ground control point is nothing but the point which is available on the satellite image and also which is seen on the ground. If you got a correlation and then using the after you have carried the correlation, some kind of polynomial equation is generated. This polynomial equation, and using a certain transformation like affine, you are able to correct the image and the distortions are removed. So once you are removing the distortion, what happens, because the signature, the sensor is with, it may be active or passive, but either case the reflected or the emitted energy or the backscattered energy passes through the atmosphere, and because of the feature which is available on the surface, you there the radiometry also gets altered. Now you require the radiometric correction as well as the geometric correction of each pixel on the image. Now there various techniques are there for radiometric correction. I've just listed, and each itself is a topic, and the method is called dark pixel subtraction technique, histogram adjustment or regression adjustment. For further details you can refer the textbook, but generally all three methods, they try to correct for various errors which are available, which have creeped in the satellite image either due to atmosphere or Earth surface features. Now let us try to learn, after the image rectification, we have to try to improve the sharpness in the image, to improve the visual interpretability of image by increasing the apparent distinction between features. It's basically to enable the user, the interpreter, to having a better image will be better, where the objects will be clearer or sharper. Now this image enhancement will be either point operation or local operation. Now try to learn quickly what kind of methods are available in the image enhancement. It will be image reduction, magnification like what we have seen, contrast adjustment, it will be linear or non-linear, band ratioing, spatial filtering, or the Fourier transformation, PCA, the principal component analysis, or the image sharpening, and so on and so forth. There are all various kind of image enhancement techniques are available for improving the contrast or the sharpness in the image. Let us take a typical example, and the most popular is the linear contrast adjustment. Here, the linear contrast adjustment is nothing but what we do, any digital number, what we find out within the image, minimum value and the maximum value. Assuming that the output data will be transformed into the 8-bit, that is the 0 to 255, output value will be computed as digital number minus mean, max minus mean. So, and then multiplied by 255, and this way we conduct the linear stretch. Let us take how this linear stretch is going to help us in the subsequent slide. Another point here which I want to make is the haze. Often what happens for varying reasons, there's a haze is there. This haze prohibits the user, interpreter, to extract the information. Now what we do based on radiometric correction method, which I have shown in the previous slide. We try to correct the image, and based on radiometric correction, the corrected image, this kind of corrected image is produced. Now let us take the example of some typical image enhancement. Now this is the raw data. You see the raw data, it is the IRS-P6 list data of certain date, and you're on the right hand side, you're seeing the histogram. I believe you know about the histogram. Histogram is nothing, is a plot of digital number versus its frequency. Now, because it's a color composite, false color composite, the 3 bands are there which are subject to the 3 graphics filters on the screen, that is red, green and blue. And band will be green, red and infrared. Once you subject the green, red and infrared, as I told in the beginning of this presentation, this way you are able to see the histogram. This is the histogram. Now, when the image is raw image, you got a histogram which is not occupying the entire range of digital number available on the screen, that is 255. It is occupying only narrow part of the display. That means what we do in the enhancement, subsequently in the enhancement we are carrying out the linear stretching, and what you see here in the histogram, you are seeing the background, the raw histogram, and in the foreground, in the red, in the green or the blue, you are seeing that the entire range of digital number available on the screen, that is occupied in the output image, and this way you are able to see the bright and with high contrast image is seen, which has got a distinct image interpretation characteristic. You can find out the vegetated surface, you can see the river, or you can see the intermittent cultural pockets, and also you can see somewhere the built up area, you can see the within the forested or the vegetated area, we can see the various kind of forested surfaces. This way, a simple linear stretching technique can help you to identify the features better. But point here, often the linear stretching technique may not be helpful because based on the range of data available, based on the scene contrast or the area is like this, that the linear contrast or linear stretching has got some disadvantage. In that sense, what we can do, we can employ certain kind of non-linear technique, and then we can do, for example, a Gaussian or the histogram adjustment technique we can employ. Like this one particular example is there where the non-linear technique has been employed. Now you are seeing the output histogram, and what you are seeing the curve here that shows the non-linear stretching which has been employed in the image, where if you compare back and forth, you will see certain areas in the image they have got highlighted and the other area is slightly suppressed, but you are able to, this way, area of interest on the screen you are highlighting or suppressing, and you are extracting the information using the image interpretation tools. Now let us move further. These kind of previously what we try to see the various kind of stretching techniques. They are the domain of contrast enhancement. But you also go for the spatial feature manipulation. Spatial means you are in the previous method you are not seeing the adjacency. That means what the adjacent feature adjacent pixel contains. Now, if you also account for, because the proximity of each pixel to the surroundings, that is also important. That is, what we do, we try to block or the pass energy over various spectral ranges. These emphasize or de-emphasize image data of various spatial frequencies. Basically, what we do, it is the same way in your at your our home. Whenever the noise comes in some audio device, we apply certain kind of filter and we suppress the noise, or we highlight certain kind of voice data, or we suppress certain kind of voice data. This way, same methodology is employed here. We try to see the using the low pass filter or the high pass filter or the band filter, where the low pass filter is designed to emphasize the low frequency features. That means the large area changes in brightness, and de-emphasize the large high frequency components of an image. For example, agricultural pockets are there. So you can employ the low pass filter, or you can use the high pass filter to emphasize the high frequency features, or and de-emphasize the high frequency component of image, large area changes in brightness. For example, you want to highlight the any kind of linear feature. It may be road, it may be canal, it can be railway line, or any feature. Then you can employ the high pass filter. So this way, how the typical filtering mechanism works, we have got a kernel, and then you got the 1 3 by 3 matrix of the original, and then what we do is certain kind of combination we make. That means what we do, we have got the kernel value multiplied by the corresponding value in the image, and this is the moving kernel. And when you find out the average, the central pixel has attained the value as 70. Originally it was 68. Then once you applied the filter, the output value is 70. So this way, what is seeing on the right hand side, you are seeing the certain kind of edge enhanced or the filtered image, where the certain features are highlighted, other features they are suppressed. Other methods are vegetation indices. Now vegetation indices, they help you to and find the various kind of vegetative surface in the built up areas, in the urban areas. Basically, you see, the green spaces, they are very important in the context of urban quality of life in the urban areas. In that sense, the vegetation indices, they are computed to eliminate the changing illumination conditions, surface slope, aspect, and other extraneous factors. They are helpful in highlighting the vegetation content in the imagery. And the commonly used variety of vegetation indices are available in the textbook, in the literature. And then you see the typical is the simple vegetation index, that is computed as VI is equal to infrared upon red, or you can compute NDVI, that is normalized difference vegetation index. And the NDVI is a function of IR minus R upon IR plus R. So this way, you see, within the vegetated area, as a ratioed image, you are able to find out whether the vegetation vigor, senescence, they are higher or lower. So this way, you can find a quality of vegetation in the urban area. You can also employ the principal component analysis. Basically, it is nothing but the principal component analysis. Based on the various covariance characteristics, you are able to repartition. You are able to partition the image into various kind of principal components. That will be principal component 1 and 2 and 3. And the later you can create the composite of the output image. And there you see certain areas will again highlighted or be suppressed based on area of interest. Now, in the context of urban planning, image fusion is very important. Image fusion is like that putting together the two kinds of information, where the each information has got certain advantage. For example, this is one pan data, that is a panchromatic data, which is acquired in single band. It is high spatial resolution, but the single band. There's another data which is coarser spatial resolution, but that is acquired in 3 spectral bands. Now mind, please pay your attention here. This is single band, this is 3 band. This has got higher spatial resolution, this has got coarser spatial resolution. If you employ a certain kind of image fusion technique, the output image will have the beauty of each input image. It will have higher spatial resolution, and also it will contain 3 spectral bands. So this way, Image fusion is it is a set of methods, tool and means of data which is available from two different images to improve the quality of information. Now let us move further. The variety of methods are available for the image fusion. Then again refer the textbook, and these methods will be pixel level, feature level or decision level. When I talk about the pixel level, when we talk about the pixel level, again variety of methods are. Then the most popular method is the IHS based, or in the statistical method it will be PCA based, or it may be image multiplicative or the wavelet, image ratioing, Brovay and so on and so forth. Various methods are available. Another method in the context of urban planning is 3D information extraction. Now please pay attention here as we try to see the shadow in high resolution images. They cast the shadow. So this here you see the building, it may be a playground, any stadium or the high rise buildings or the any kind of tower. Each object has casted some shadow. So based on the trigonometric rule, we can find out the height of the object. The height of the object will be length of the shadow multiplied by the solar elevation angle. So this way we can compute the height of the object. Now people are experimenting that how to do the automation or how to find out the height of the objects, built up areas, and the methods are, variety of methods are available for finding out the heights of 3D objects in urban areas. Now move further, that now I come to the information extraction. So all these, because we have seen that how using the visual interpretation skill and the elements of image interpretation, you can extract various kind of information in the urban areas visually. That means the interpreter is sitting with the manual method. Yes, put the imagery on the light table, put the tracing sheet, and the information extraction is happening. But also you can employ the machine-based algorithms. The machine-based algorithm means digital data is available, and then you train the computer, and then either you can training the computer using the supervised classification technique, or you can do the post some kind of automation, again you can do using the unsupervised classification technique. Basically the supervised classification technique, when you employ it, is nothing but the a priori knowledge is used to train the classifier. How we get the a priori information? It will be based on some past knowledge about the area. It belongs to certain city. Now we know which part of the city it is, what kind of feature it is, and then all otherwise you can visit the ground, and then the training sets are identified for the classes present. And then based on the statistical training set, the pixels are classified. In the case of unsupervised classification, now what we do some kind of automation, and then we generate the clusters of spectrally similar groups. And these clusters are helpful for the unsupervised classification, and later on the classes, signature clusters and number of clusters what has been generated, and the same cluster can be assigned to certain classes. Now let us take what the process, try to see the process of supervised classification. This is the image is there. Now you've got known built up area, this is known water body, this is known agricultural area. Now what we do, we train the computer. So we train the computer, and then some built up area, we say part of this built up area, this is built up area, part of this body, then in the training signature we generate, we say this is water body, then we say this is the agriculture. Now you see you have trained the computer in a minimal way, and then using the certain kind of statistical data and technique, and using one of these method, and this method will be minimum distance to mean, parallelepiped or maximum likelihood, where the maximum likelihood is the most popular method, and then the entire image will be classified, and the entire image will be converted into the output image. If you using the unsupervised classification, now what it does, the analyst requests the computer to examine the image and extract a number of spectrally distinct clusters. Now what we do, we say this is one kind of a cluster, This is second kind of cluster. This is third kind of cluster. And then we got the clusters. Now these clusters later on, what we do, this will be, we say, what you see in the blue color. Again, within the blue color, we have got two clusters. So this will be water. Again, this will be such other kind of water. The green color, again, the light and dark green will be forest type 1, forest type 2. And then within the agricultural area, that will be culture, or it may be scrub or certain other kind of vegetated cover. So this way, you can use the supervised classification technique, or you can use the unsupervised classification technique, and then you can do the information extraction. Now, both of these methods, they have got certain advantage or disadvantage. In the context of maximum likelihood and the supervised classification, it is good, fine, only minimal training is required. It does good separation of the classes. It requires strong training sets to accurately describe the mean and covariance structure of the classes. Then comes the unsupervised classification. It takes a maximum advantage of spectral variability, but it the demerit is it requires the maximum separable clusters in spectral spaces may not match with the perception of the important classes on the landscape. So this way, each method has got some advantage or disadvantage. There are certain other advanced classification techniques are available. For example, neural network, which uses flexible, not necessarily linear functions to partition spectral spaces. Or one can use the contextual classifier to incorporate the spatial or temporal conditions, or the object-oriented classification scheme to decompose scene into many relatively homogeneous image objects. They are all called as patches or segments, using a multi-resolution image segmentation process. So each is topic is a subject itself. Those who are interested, they can refer the textbook further. Now, once we have generated the output image, whether it is the output of visual interpretation or it is the output of digital image classification. Now, the question comes accuracy, because any kind of output which is generated, it carries certain kind of accuracy tag. And the accuracy will be spatial, thematic, topological, or temporal. Spatial means what is the planimetric accuracy. Thematic means whether the classes, the way they are classified or interpreted, do they belong to the same category on the ground. Topological means related to the GIS. That means whether the topologically they are whether the topological characteristics they are maintained. That means connectivity and adjacency has been maintained. Whether the temporal characteristic means when you have got a temporal image, whether they are temporally co-registered well, the information is discernible. So this way, each has got the accuracy tag, and accuracy assessment can be carried out. Now let us see how the thematic accuracy can be found out. Now this is a typical confusion matrix which is generated. Now this confusion matrix is generated based on, let us assume there are only 4 classes, that is in the given built up area and the surrounding regional area, 4 classes we have segregated, that is forest, agriculture, scrub, and built up. You see the diagonal plexus, they are correctly classified, 65, 81, 85, and 90. And the off diagonal classes, they are erroneous, and this will be constitute the producer's accuracy or user's accuracy. The overall accuracy is nothing but summation of the diagonal classes upon the total number of pixels. You see this particular classification has got an overall accuracy of 74%. And the producer's accuracy will be, based on 65 upon 75 for the forest, 81 upon 103 for the agriculture, 85 upon 115 for the scrub, then 90 upon 141 for the built up area. This way, the producer's accuracy and the user's accuracy is computed. But one can also compute that beyond not only the overall accuracy, but also there's another important criteria is that is called kappa coefficient. It reflects the difference between actual agreement and the agreement expected by chance. So kappa, for example, if you obtain 0.85, that means there's 85% better than agreement, that is by chance alone. So what we do, observed accuracy, which we have computed in the previous one, and the chance agreement, and once upon chance agreement. So this way, the chance agreement is the diagonal element, and this way we compute the kappa accuracy. So using which we can generate the output products. Now this sums up the methods how using the digital image processing method or the visual interpretation techniques method, we can derive the information which is useful for urban and regional planning. So this subject is very huge. This cannot be covered in a session of 1 hour or plus. But I assume that at least I have to able to generate or I have to pass on some kind of knowledge. Or further, you can read books are available. And what I recommend popular books like Lillison and Kiefer or the Jensen or many of the books are available for further knowledge. Thank you very much.